Good morning. Let me start by thanking Ihsan and the other organizers of this workshop for inviting me to give a talk about our work that is related to learning from instructional videos. And I've titled the talk as Learning from Narrated Videos of Everyday Tasks. And I've made that expansion to show you that videos associated with narrations can come from two sources of videos. The first is instructional videos available on platforms such as YouTube, where there is the video and immediately the person is talking over the video to give you instructions. So this is one type of narrated videos. The other type is where videos have been narrated after they've been captured, and that's something we've done within Epic Kitchens, the dataset I'll tell you more about if you don't know about it towards the end, where you have the video, you have the narration, but that has been acquired after the video is collected, allowing you to do your actions very naturally. While in instructional videos, people tend to slow their actions to allow them to explain on the fly. And during the talk, I will gather a bunch of papers that we've done with these types of narrated videos, and I've grouped them in three categories. One, works that combine video or vision and language, then skill assessment from video, and finally using narrations as a source of weak supervision. And let me start by the first work, which is a work that will be presented this week, supposedly when you see this video, in CVPR, and it's called Learning from Adverbs in Instructional Videos. Right, so in this work, we're using purely instructional videos from How to 1 Million dataset. That's a large dataset, which we kind of scaled down to focus on 81 tasks and around 100 videos per task. But here we are looking at the whole narrations and focusing on learning adverbs. Why are adverbs interesting? Because they give you a finer grained understanding of how the action has been performed. Usually people associate adverbs with instructional videos when they want to give a particular comment, like make sure you do this slowly, make sure you dissolve this completely. So identifying adverbs and learning adverbs allows you to focus on these tasks, which are very crucial in performing tasks that are within these instructional videos. So let's see an overview of this work. So you have videos associated with these narrations, and we focus on the narrations that include adverbs. We use an embedding space, so that's a video text embedding, where we have already texts that represent actions. So these are word-to-vec embeddings of these actions. And then we want to embed the video, but focus on the parts of the video that are relevant for the action. For example, there is a long video, but we want to focus on the bit where the person is slicing finely. So we're using slicing as a query to focus on those bits in a weakly supervised manner. Then we want to embed that video, but it's not a typical slice, it is slice finely. And that's where we're proposing to learn these adverbs as transformations in that space, and that these transformations apply to multiple actions. So we can spread finely, we can also slice finely. And that allows us to learn what finely is, independent of the action. And similarly, you can learn more adverbs. And some of these could be antonyms, like finely, coarsely, and that's really helpful in learning. It's a good regularizer in learning. But also you can learn other adverbs like quickly. And notice that these are not supposedly, so you can do finely and quickly, right? So some of these could actually be concurrent. But the labels that come with the video, the narrations, will only particularly mention one of these. So only finely. Right, so this is the overview, and let's tell you a little bit about the method. So we start with the video where we have parsed the narration to take the actions and the adverbs. And we want this embedding space that embeds the video close to the transformed action. So if we have the embedding of the action, let's call this G of A. What we want to learn is a modifier, a transformation in the space that makes the modified action close to this video, because the video doesn't explicit rolling in this example, it represents rolling quickly. And this on its own is a challenging task where we apply these action modifiers to multiple actions. But in this case, learning from datasets such as How to 1 Million, we have the additional complexity of learning with weak supervision because we haven't labeled exactly where rolling is within the video. We just have this rough alignment between the narration and the video. And sometimes people might mention sentences like start by rolling quickly, but they might not even include that action altogether in the video. So in this work, we start by extracting i3D features from a window around the narration. And then we want to use a transformer, so an attention module, to attend to a particular part of the video. What do we want to attend to? We want to attend to the parts that represent the action rolling. And that's why we use the word-to-vec embedding of the action as the query. That allows us to focus on the part of the video that represents rolling, and then we want to embed that close to the modified action rolling quickly. I'll show you some qualitative results first, and the video will have a boundary around it, and that boundary will be thicker when the video attends to the action mix. So in this case, we have the video, and we know that we're focusing on the word mix or the action mix, and then we want to kind of predict the relevant adverb. So the video will be thicker in this correct recognition task when the person is mixing, and then these particular segments are being used to predict correctly the adverb, in this case, quickly. Let's take a few examples. If you want to watch this video, you can watch it on the full data set. This is turning quickly, and again, the video is thicker, the boundary is thicker when you're attending to the bits that include turning, and then you predict the action turning quickly. Right, all the papers I'm going to tell you, if you want more details about the methods, the results, the code, and the data, there is a web page per paper that you can refer to. And for this paper in particular, you can join in the first session of the conference on Tuesday morning to talk more to Hazel one-to-one about any questions you have about action modifiers, learning from adverbs in instructional videos. The second bit of work, where we also looked at vision and language in the context of narrated videos, was presented last year in ICCV. And what we want to do is a retrieval task. So either we have a video and we want to retrieve the caption or the narration, or we would have the narration and we would want to retrieve the relevant video. And there are lots of works that have attended retrieval or video retrieval in the context of instructional or narrated videos. However, they tend to take the caption as is in one go and embed the whole context of the caption. In this work, we attempted to learn multiple possible embedding spaces using the knowledge of the part of speech of that caption. So similar to the work we've done with adverb, where we parsed the narration to focus on verbs and adverbs, here we parse the narration into its verbs and nouns, and we show examples with different types of part of speech. Then we embed the visuals with the verb embedding in a verb embedding space. We also take the same video and have a different function that embeds it in a noun embedding space. Given that it's the same input video, you can see that these functions are going to learn different things. They're going to learn features that represent the verb or the action in the first space, and videos that represent and features that represent the objects in the noun embedding space. Once we learned these spaces in a triplet manner, then you can combine the information from both spaces into an action space. So you take the visual representation from the verb embedding, the visual representation from the noun embedding, that's the visual action embedding, and similarly for the text embedding. And we learn these end to end. So we learn the part of speech embeddings as well as the action embedding together. So more specifically, as we said, I have the same video, so the same feature of the video, but we have different video embedding functions. And then we parse the segment into its, let's say in this case, verbs and nouns, allowing to learn a noun embedding space and a verb embedding space. Then these are jointly then used to learn an action embedding space. We call this approach the joint part of speech embedding approach, JPOS. And the results show that regardless of what type of approach you use, whether you use the full caption, only verbs, only nouns, or their combination, and this was tested on the Epic Kitchens dataset, the approach of using multiple part of speech embedding always outperforms the individual embeddings. And it also outperforms prior approaches like CCA as baselines. We also tested this on other video retrieval datasets like MSR VTT. If you want more details, you can refer to the paper. I would like to show you, though, a bit of a video that shows what do we mean by learning different embedding spaces. So this is a maximum activation example. So we're going to show you the videos that maximally activate a particular neuron in the noun embedding space versus in the verb embedding space. So this is a neuron in the noun embedding space, and I'm telling you here, it looks like it's learning cutting boards, because all of these are cutting board videos, but with different actions. So it had grouped all these into a particular neuron. Similarly, if you look at the verb embedding space, you see that it had grouped video segments that represent opening or closing, but with multiple actions. And that's really what we wanted. We wanted to understand the action versus the video. And you can look at the paper for more details, as well as these videos online, to see how you can achieve much better retrievals as part of the work. And this is like a bit of information for the future. We will be releasing video retrieval as an additional challenge alongside Epic Kitchens if you've used it. Right, so in the first part, I told you about vision and language. And I mentioned a few examples of what we've done with vision and language, but focusing more on parts of speech, adverbs, and then multiple parts of speech embeddings. I'll then tell you about a work that we've started a couple of years ago now, and the latest publication was last CVPR, on understanding skill in long videos, in long instructional videos. So that means we are taking multiple videos of the same task, and our intention is to assess the relative skill of the performer in the same task, but in a collection of videos. Currently, if you go to YouTube and you search for these instructional videos, how to roll a pizza dough in this example, you'll get a ranking, but that ranking will probably depend on whether the person is a celebrity or is funny or is popular, etc. Here, we want to objectively assess the skill level in the video. And we've tested this on a variety of videos. Some we have captured and some from instructional videos in YouTube. But the first bit is to annotate. So we give crowdsourcing, so Amazon Mechanical Turkers, a pair of videos, and we ask them to assess whether they believe one video is exhibiting a higher level of skill than the other. And by watching the video, they will kind of study the task. And if multiple people agree that one video is exhibiting a higher skill, then we consider this ground truth, and we use this both for labeling and for evaluation. It's worth noting that this concept of understanding skill has been assessed previously in videos such as Olympics tasks, where the input is an Olympic performance and the output is the score of the judges in Olympics. So it's a regression task. But of course, the problem with these tasks is that you would need an Olympic committee to decide these scores. And hopefully, you don't need an Olympic committee for things like rolling a pizza dough. And you might not find anyone who would agree on an Olympic committee for drawing, but you will find people to agree that the person on the right is exhibiting a higher level of skill in this copying drawing task. Once we've learned using these pairwise annotations, we can actually rank all the videos from best to worst. And these are videos we've selected. We have 100 videos in the test set. These are videos we've selected on applying eyeliner. So what's the approach here? The approach is the input is a pair of videos where one has been annotated as being higher than the other, and we're using a CME's architecture with an i3D extracting features throughout the long video. And then we would be accumulating these features and learning a ranking loss that attempts to generate an output that ranks the first video higher than the second. This is a CME's network, so weights are shared. And if we then input multiple pairings of these annotated videos, we will end up with what we want, a final ranking of the various videos after training. But these videos tend to be long. And that means many segments in that video might not be skill relevant. In the example you see here of braiding hair, you might see sections of the video that represent just combing the hair, and that might not be skill relevant, probably is not skill relevant, but there are segments that are related to the braiding itself that will have a more significant impact on you analyzing the skill level of the performer. So in this work, we added a temporal attention module that learns to weight these various segments by their relevance for skill determination. And we have a regularizer that ensures that our learned weighting outperforms uniform. And that does not improve performance, but it stabilizes the learning. After we've done that, which is probably what people would think if they want to learn some ranking in samples, videos, or images, we realized that for particular segments in the video, mistakes have not been picked up as parts of the video with high weighting. So they were not really weighted highly in deciding the final ranking. And that's counterintuitive because you would think mistakes are your best evidence that this person is not really highly skilled. And the reason this is happening is because of the CME's architecture and the shared weighting. The fact that you are not really looking for mistakes that appear in some of the videos, but you're looking for how to weight subtasks that appear in both types of videos to allow the network to focus on mistakes or what's really good that might not really appear in all the videos. In this work, we propose to use 2 attention modules. And until now, they're exactly the same. They learn exactly the same until you introduce a rank-aware loss. And this makes them specialize. This makes one attention module specialized to learn what's good in the video, and the other specializes to learn what's less good in the video. And that's why the paper is entitled The Pros and the Cons. Let's see what these attention modules learn. And this is an output of learning, so there is no input here that we've fed. These are parts of the video that have been selected as evidence of low skill in a variety of tasks. And if you look at origami at the end, then all these examples that have been given high weighting for low skill are someone who's undoing the fault. So they're undoing what they had done. If we look at examples of high skill, then in the last row again, you see people stopping and hesitating as they're drawing. And interestingly, in drawing, that's evidence of high skill. You would see in other tasks that the same behavior, which is stopping to consider what you're doing next, is evidence of low skill, like in applying makeup, right? If you pose, you probably don't know what you're doing. But in drawing, if you pose, you're probably considering how to draw rather than just you're drawing the next bit. And the paper will have lots of details about the importance of these different losses, as well as for the various tasks that we've tried, some from YouTube, some we've captured, and some are surgery tasks that have been publicly available and used for skill assessment previously. You'll see the various levels of the various parts or components of the model and their contribution to the final pairwise accuracy. Right, so until now I told you about approaches we've used to understand vision and language, and then approaches to understand skill. Skill is not using the narration except to select the task. And finally, I'll tell you about using narrations as a form of weak supervision. And I'll start with the work we also presented last CVPR. It's called Action Recognition from Single Timestamp Supervision. Let's look at what these narrations are. And these are narrations in this case from Epic Kitchen. So these are narrations captured after the videos have been collected. And if you basically pass them via YouTube's ASR, then you will get these sentences saying, at minute 6, someone said, close this water. At 6:03, someone said, fold the kitchen roll, right? So you have these single timestamps. Interestingly, if you look at the video around these single timestamps, they're not always, this is not a corresponding example, but they're not always aligned with the action itself. They could be before the action, slightly after the action, and overlapping with the action. What this work is attempting to do is to start from these single timestamps, but then modify these proposals of where the actions take place so that eventually you not only align to the right action, but you learn an action recognition model. This is not a localization task. This is really, how can I learn examples for action recognition, but from single timestamps? You can consider this as a way to do localization. However, typically localization tends to try to know what you want as start and end times for actions. If you want more details about why this is not a localization approach, but a bit that learns the most discriminative parts of the video for a classifier, for an action recognition model, you can look at the paper. But let me tell you the intuition of how this work updates, and the code is publicly available. So we start with these single timestamps, and then we have this proposal that says most probably the action is around here. And we can kind of decide the extent based on either some heuristics or based on how close by, nearby, how close by other actions are before or after. With learning lots of examples of, in this case, opening the fridge, then you can learn an action recognition model, and then you can pass this video again. This is the initial proposal, and that gives you a weighting, a softmax score per frame, or whether this could represent an open fridge action. Then we would update that proposal and learn another classifier and keep updating until we converge over lots of iterations. And of course, this assumes that this is not the only example, right? There are lots of examples of opening fridge with lots of single timestamp supervision. And this over time results in learning the right action. And I'll show you a video of the outputs applied in this case on Epic Kitchens, but we've tested this on multiple data sets. The thick horizontal border in the middle, this is the ground truth. And then you're gonna see the initial timestamp and the updated timestamp over time. So over time, these proposals are being updated in size and location. And by the end, you'll see what the action is. So this is the first one, which is open drawer. Sorry. And it was a long action. And after updating, it's the exact action. And I'll see the third example. So the third example is moving bottle. And then after learning, you get exactly the most discriminative parts of the action. This is another example also from Epic Kitchen, and you'll see how dense these actions are. Put lid, wash spoon, wash fork, and put cutlery. So that's the long put lid. And now we have this very short action of the most discriminative part. This is wash spoon. This is wash fork. And finally, you have the put cutlery, which is now being refined to the exact putting action. A third example of opening cupboard. It was very far to start with, and after time, it's actually getting very close to the cupboard. And again, if you want to see that video or look at the paper, please feel free to look at the webpage of that paper. And finally, before I conclude, I want to tell you about the Epic Kitchens dataset, which is, again, I'm sure over the course of today, you will see a number of these narrated video datasets. Some come from instructional videos online, and some come from what we call natural videos, like the Epic Kitchens dataset. So Epic Kitchen is a collaboration led by the University of Bristol, but with collaborators in Toronto and Catania. And in this work, we started by giving cameras to individuals and asking them to record everything they've done in their kitchen for 3 consecutive days, giving us the largest dataset in egocentric vision or in wearable cameras. The largest and I believe the most complex, because we have started by this data collection exercise, asking people to record everything they've done in their kitchen, all the way from preparing their coffee in the morning to washing the dishes in the evening. And that gives us this natural recording in people's native environments. And if you're performing a task in your kitchen, you will definitely be far more agile than if we take you to a smart environment or a kitchen you don't know. And this is not really giving any script. This is just preparing your normal breakfast or dinner. But of course, these types of natural interactions are very hard to annotate because they're unstructured and they're very long. These videos range from you being in the kitchen for 10 minutes to 2 hours if you're preparing a complex meal. So the paper is about scaling these types of natural interaction approaches by asking people to talk over their videos after they've recorded them. And as I told you, this is why this is a narrated data set in some source. So with each video, you have a subtitle that had been given by the individual, and that subtitle is in their native language, because after we started the collaboration, we realized that even if you've been in Bristol or in Toronto for a number of years, and you are dealing with English on your daily life, you don't know the name of a particular ingredient or a particular utensil in English, because you don't need that. You know it only in your native language. So we asked people to narrate in their native language. We have 5 different languages, which we've transcribed and translated. And we offered the translated version as narrations. If you want to use the multiple language one, you can refer to us. We can give you the other languages. However, we only have 1 language per video rather than multiple languages per video, because each person narrated their video in their native language. From these narrations, we went and refined the start and end time of action segments. And we also went and ground truth the bounding box of the active object. And currently, as I'm speaking to you, there are 3 sets of challenges. As I'm speaking to you now, because I'm recording this before the end of May, there are 3 open challenges, but by the time you watch this alongside CVPR, the challenge winners would be advertised. And the most standard challenge that we have is action recognition, but we also have action anticipation and object detection. So Epic Kitchens was released in 2008, capturing people in 32 kitchens, a single person environment in 4 different cities and 55 hours. Very soon, actually on the 1st of July, we are releasing an extension of this dataset, adding 45 hours, making it a 100-hour dataset. And interestingly, we introduce a bunch of interesting ways of collecting and annotating the dataset, including asking 16 of our 32 original kitchens to record again. We also have 5 new participants. Out of these who've recorded again 2 years later, 8 of them had stayed in the same home and 8 of them changed homes. So you're having participants that are new, participants that are returning in the same environment, and participants that are returning, it's their actions, some of their utensils, but it's a different environment. Right, in both Epic Original and Epic Extension, we have these narrations, and we have them in people's original languages. And after that, we went and asked Mechanical Turkers to move these single timestamps to decide on start and end times. We also parsed these narrations to define verbs and nouns. And this is the type of action segments I showed you initially. And you see that some of them happen in parallel, right? So you see, it's not only one action. We actually have in the extension, around 50% of the actions are overlapping. And we also have some actions like tying the bag for the bin. And that's not something that people would have collected in other data sets. It's only the natural interactions that allow you to collect. The new extensions has been refined for even denser annotations. As you can see in the example here, on average, the original set of videos had 13 actions per minute, and the extensions have around 20. And the number of overlapping actions increased from 23 to 56, and you'll have to wait a little bit for the paper to see, probably it will be on an archive very soon, to see how we ensure that we have increased density and tighter annotations. This is allowing us actually to use Epic Kitchens for action localization. And if you're interested in that, there will be more information coming very soon. Actually, on the 1st of July, we will have a live webinar that tells about how we collected the extension and how people can use Epic Kitchens 100, which is the extended version of Epic Kitchens. Of course, part of the task of dealing with narrations is the variability in the usage of verbs and nouns as people describe the actions. So you would see people saying, take, grab, pick, get, fetch, pick up. And we had to manually group these into action classes. And there isn't really a way to do that in any automatic way, because a word take will end up in word2vec closer to the word put than the word fetch. That's the nature of how corpuses have been collected. Similarly, we had a combined automatic and manual stage to group nouns like Parmesan and mozzarella into noun classes. Despite all this grouping, we still have 97 different verb classes and around 100 noun classes. And we have a heavily long-tailed distribution. In this case, you'll see in faded, the original annotations come from Epic 2018 or Epic Kitchens 55 hours, and then the extension Epic Kitchens 100. So you'll see how much we've scaled each class. You'll also see the long-tailed distribution in both verb classes at the top and noun classes at the bottom. And note that the y-axis here is log-scaled. So this is heavily long-tailed. That's the natural interaction. You're going to open the fridge 10 times more than cutting a cucumber. And if you want more details about the dataset, as we said, overall the dataset currently has 100 hours, 700 videos, around 90,000 action segments, 20,000 unique narrations, grouped into 97 verb classes, 300 noun classes, and a large number of combinations, so around 4,000 action classes. We will also be releasing on the 1st of May, lots of automatic annotations of object masks, hand and object bounding boxes, and these are using a model generated by the University of Michigan, which is also going to be presented in a paper at the CVPR. As I said, there are 3 open challenges at the moment, and the set of winners would be announced basically on the day you listen to this video. So you can refer to the Epic Kitchens webpage to understand, or well, to follow up on the winners. And the action recognition challenge, which is the most basic one, is really taking a trimmed action segment annotated by Amazon Mechanical Turkers and attempting to predict the verb and the noun class. However, the Epic Kitchens dataset, as you've seen, with its untrimmed nature and narrations using free-form language and also multiple languages, lends itself to a lot of variety of tasks. And we have been seeing over the past year, lots of people using Epic Kitchens in more than the challenges we had set, the basic challenges we'd set. We have a CodaLab leaderboard you can follow, and we also have released models for action recognition using some standard approaches like TSN, TRN, TSM, and these models are publicly available along with their performance optimized for Epic Kitchens if you want to use the outcome of these to predict something higher level like activities or progression of actions. If you want to know more about Epic Kitchens, there is the Epic Kitchens webpage, and also there is a mailing list that you can subscribe to. You can also, if you're working on anything to do with Egocentric Vision or Epic Kitchens, you can also submit your news, whether you have annotations or code or papers that are related to this dataset. Right, before I conclude, having told you about all the papers that are relevant to learning from narrated videos, I want to thank the team. I get the pleasure to come and presenting this collection of interesting ideas, but there is a big and I wouldn't say very big, but a very active team behind Epic Kitchens and all the sets of papers I told you about. If you're interested to know more about the group's work and our papers, please visit my webpage. I keep an active Twitter account. We have the datasets, the code, and the publications available. I'll end up by thanking you for listening to this. I know that you will be listening to lots of recordings this week of different keynotes, and I hope that you've enjoyed this one in particular. Thank you.